study inside seismic hazard study, and they came up with this spectra. So you can see here, this is spectra, the elastic response spectra for damping ratio of 5% of for the earthquake of 2% in 50 years. This is a spectra. For the earthquake of 2% in 50 years, this is a 10% in 50 years. This is a spectra.
In order to make sure that the structure needed to be retrofitted, so people from Ecuador did just response spectrum analysis, elastic analysis, but we didn't have that, so we redid that in order to make sure about the answer that they had. So we decided to use 18 modes, and we completed the mass participation in both directions, almost 100%, and we considered the model combinations using as stated in the Equatorian code. So as you can see here in this red dash, you can see that all of both values are more than the 2%, which is the maximum limit that you can consider in the Equatorian code, is similar to the code, American code. So after that, we decided to get to make a deep analysis to the structure. So we did a pushover analysis, in this case static, and after that a nonlinear dynamic analysis. So in this case we started to define how would be the component model. So we decided to use this concentrated plasticity and plastic hinge, and we developed this model in tabs. Okay, first of all, we needed to consider how would be the behavior of the hinge in each section. So we follow what is stated in the ASCE 41. So here is number one is when the section yields, following by a strength hardening. So in order so that the program can know about the steel reinforcement that was in each section, we added to the program the exact quantity of reinforcement, upper and lower reinforcement. And about the member stiffness, we follow with what was stated in the ASCE 41 as well. So for beams, non-pressures, we consider 0.3 the value of the elastic rigidity. And for the column, we created a table with in order to have the ratio between these values. So as you can see, we have almost 0.5. So for that reason, we continue with this flexural rigidity for the columns. Okay, for the modeling parameters and numerical acceptance criteria, for in this case for reinforcement concrete beams, we following as well what is stated in the code, but we decided to take the worst case. So we wanted to control that to the structure in this case. This is for column. Okay. Okay. In order to make sure what the model in ETAPS was doing, so we decided to not use the default option, and we decided to continue calculating the yield creep, which is given by we use the formula of the Professor Priestley. You can see here the correlation that he did in order to find this value for reinforced concrete structure. And we calculate this yield rate for each beam, and grouping the beams by similar length and similar depth in order to reduce this calculation. And we did the same for the columns. So, and we added this value, for example, this value, we added in this way to get the load deformation curve for the hinge, and we normalize the acceptance criteria with this value.
Okay, so you can see here, this is a rendering of the building, which is, they are not complicated structures, simple structures, and we did in ETAPS. So we got here the fundamental periods in each direction. For the x direction, we have 0.84 seconds, and for the y direction, we have 1.51 seconds. So we started to do the pushover analysis, and we are going to show you step by step. So here's the gravitational load, 0 step, then the first step, and then the hinges start to form here. And we can see in the third step, we consider that it reached the nice safety level because you see a considerable amount of hinges that have this color. So this is subjective. So for this is step 4, we continue pushing it to see what's the collapse prevention level, and we determined that the collapse prevention level was here. So you can see that there are a considerable amount of hinges of this color. We also did the same in the Y direction, and in the previous one there was the life safety, and this is the collapse prevention level. The results that we got are here. Here we have the pushover curve in the X direction, the pushover curve in the Y direction. When we got that, we calculated the target displacement, which is in this table, but I'm going to explain it to you in the next slide. So here, the yellow dot represents the target displacement calculated according to the code, and the green dot represents where the displacement of the pushover curve for the 475 years return period. So as you can see here, the displacement according to the pushover lies behind the target displacement, so that is not acceptable according to the code. So, and we have the same with this period here, with 2,500 years. This one is the pushover, so it lies behind the target displacement, which means that the structure needs something like to be retrofitted. So this structure had to be retrofitted, and following this, we decided to retrofit the structure, taking into account the solution dependent damper. So in this case, this is a gel damper, which releases energy. In this case, the force in this damper are proportional to displacement, and in this case of damper, we take advantage of the theoretical figure of this in order to, when it heals, so it releases energy, so reducing the loads supported by the other structural elements. So in this case, you can see one sample of this kind of devices. So here you have two braces, and this is the damper. So in this case, it will heal against shear forces. So this is the distribution of the damper putting in the structure. But in this case, we are showing you the input that we put to the gel damper. So we decided to take the just the gel direction. So we use U2 and U3. And for the nonlinear properties, we decided to add 20,000 tons per meter and a gel strength of 80 tons. So you can see here the structure again, but with the solution implemented. And you can notice that there was a reduction of the periods of this is Y. In this case, for X and Y, because of the damper, in this case, the bracer. And again, we developed pushover analysis, static analysis. You can see here the life safety level reached, collapse prevention level reached, and the speed level reached for the Y direction. So here we have the pushover curve, and we developed the same procedure that Andres explained. So here it happens, it's the same as I just explained, but it happens here that this dot is in front of the yellow point, which means that it meets the criteria. It's in front, like it can get to a higher displacement according to comparing to the target displacement. That's this for the 475 years. For the 2,500 years, it happens the same way. This point lies in front of this point, so that's acceptable according to the code. Okay, after the results were done, so we started to verify if the dampers were working. So for that reason, we plot the shear forces, and we make sure that it was not above the 80 that we added to the program. So here we can see that at most the dampers were taking 80 as we put in the program. So here we have the monotonic curve, which represents at most 80 tons. So after that, we decided, as Ronnie said, we performed the nonlinear dynamic analysis to see more results about what we're doing. And here we took the 7 earthquakes that Reagan sent us to work with, and we scaled them. Like for the 2,500 years, the scale factor was 1, and the scale factor for the 475 years was 0.63. So we tried to work with the direct integration method in the ETAPS, but it always crashed, and so we couldn't work with it. So the ETAPS also offered this option, which is the fast nonlinear dynamic analysis. So this is the equation that the program works with. So what it does is that it separates the K elastic matrix from the nonlinear curve, nonlinear forces in order to not calculate the K matrix again. So this has the ground motions, and the advantage of this method is that it satisfies equilibrium, force deformation, and compatibility relationships. So this is the results that we got. Like this, we have here, for example, the normal period earthquake. It will behave that if, for example, here you can say that it is 45 millimeters that it will be the maximum displacement. And if we go to the curve here, you can see that it will be here. So according to the pushover analysis, this point will lie behind the flight safety and the collapse prevention. So it will have a good behavior on this earthquake. The same with the Northridge. It's the same analogy. It will lie around here, so behind these 2 points. And also,
in addition to this, we wanted to again to make sure that the structure were working. And you can see here that there is not here of the number. So here is releasing energy, and if you calculate it, this slope is exactly the 20,000 that we added to the program.
okay, according to what we did, we have this conclusion. So the initiative of this upper retrofit structure worked
For this structure, well,
the structure will perform according to the criteria given by the ASCE basic safety objective. The capacity of deformation of the structure is greater than the demand of displacement for the life safety and the collapse prevention levels. And seismic response of the structure was reduced by taking advantage of the hysteretic behavior of the yield dampers in the inelastic range, which dissipates a substantial portion of the input energy. So, and as for our recommendation, after what we just did, we recommend to complete the retrofitting process, analyzing element by element to see if their nominal capacity is above the ultimate forces that the structure is subjected to. Thank you very much.